So you're just gonna throw it away, so you might as well tear it apart.
Well,
Why do you have to ask?
Yeah, why are you asking to do that?
Because I'm a civil person.
There you go.
Throw the box away. Rip it up.
Maybe it needs to be recycled.
Yeah, well, I don't think so.
All right, here we go.
Good
point, John.
Wow, 3 lazy people came up with their.
Phones, phones, phones.
What?
Okay, yeah, we are going to, let's talk about this real quick on the lab. So here's kind of a, you ready? Tell me when you're ready. We good?
Aye, aye, Captain.
All right. So this represents the lab, right? So there's the track. Here's where we're measuring the height, right? So we're measuring, you'd have your meter sticks up here, and you're going to measure the distance from, at some mark on the track, you're either going to measure the distance to the top or the bottom, it doesn't matter, of the track. Do the same thing over here, and the difference of those would represent the height of the incline, right? Over that length of incline that you've measured. Either it's, maybe you go, so hypothetically you go from 10 centimeters up to 110 centimeters, so it's 100 centimeters, right? So there's the length, there's the height. What we want to do then is we want to calculate in the data table. Let me just pull up the data table here. Let's see, where was this? So in this data table, look what they're wanting on this. See, look, they're actually, they don't want theta here. They want sine theta, right? So what is sine theta? If we go back and look on here, sine theta, if that's the angle theta, by SOHCAHTOA, what is sine theta equal to? Okay, yes, opposite over adjacent. So that's going to be the measurement of the height divided by the length, right?
Not actually sine theta.
No, it is. That is literally sine theta. Sine theta is equal to that ratio, right?
But do you actually put it in sine and then what do you?
No. That's, see, you're not,
Yeah, that's what
you don't know what theta is the point, right?
Yeah.
I mean, you could take the arc sine of that ratio and find theta, but there's really no need to. We're just looking for sine theta is really all we want. So sine theta is just going to be the ratio of that measurement divided by that measurement, right? Okay? And it's going to be small, isn't it? I mean, that height is a lot smaller than the length. So if we look, let's just look at this for a second and see what happens here. So everybody can see that, I hope. So this represents, here's the table, this represents the track, and that represents the height, right? So look what's happening. If x is the angle that we're looking at, that's the x right here is at 12.38 degrees. If I move this down, x gets smaller. Everybody see that? Okay, well this is calculating the sine of angle x. It's literally calculating that, like putting it into the sine function. Look what we've got over here. We're measuring the length of AC corresponds to the height of the track. Obviously this is kind of, these are weird measurements. These are a lot different than yours would be, but it doesn't matter. It's irrelevant. Maybe we made these meters or something instead. The measure of angle between A and B is going to be that distance. And if I take the ratio of those, the measure of the segment AC divided by the length of segment AB, notice that that's exactly equal to the sine of angle X, isn't it? It stays the same the whole time, right? Okay, so what we really want to do then is we've got this data table that you're building, right? You've measured on your lab, you've got these measurements, and I've got some sample ones here. If we go to, here's some examples of some values of sine theta that are reasonable, realistic, probably very similar to yours. And the accelerations, the average accelerations that you measured with the motion detector, right? You took 3 trials of each and averaged them, right? And what we really want to do then is we want to look at what's the acceleration as a function of sine theta, right? Okay, so when you graph these things, I'll show you a couple little tricks I just learned when I pulled this thing up on here. For one thing, notice all my data points are way down there. That's not very convenient. I want to spread those out when I get my best fit line, right? So one thing you can do, you can go in and manually change these, or if you just click up here at the top, you can type in what you want the top to be. So let's see, like that's going to be about what, 0.45 seems about right. No, there's 1 right there, isn't it?
Yeah.
That's 1, so we'll go about 0.9, something like that. Oops. Okay, and it spreads them out. Okay. 1, 2, 3, 4. There we go. Okay, so I could even go 0.8, couldn't I? Let's go 0.8. What about over here? Well, they're all crunched up over here. If I look at my acceleration numbers, the biggest one is 0.685. So if I went like 0.7 down here, oh, that didn't work. What are
That
the?
signs you want point.
Oh, I got it backwards, didn't I? Yeah.
0.09.
Whoops, I got this totally backwards. So I want this to be. Yeah, I've mixed those around. So this one should be about 0.7. And this one down here should be about 0.09.
0.09.
09. Oops, I thought I typed an O there. There we go. Okay, that makes sense? So there's my data points, and now if I want to get a best fit line, I think I have to grab those data points like that. And then I just go up here and go best fit line, and it calculates a best fit line. Okay? Okay. So,
And then the slope is just the graph acceleration.
okay, well, I mean, we'll talk about that. But wouldn't it be nice now, on this model that I've got here, right? On this model that I've got, and that's a pretty good correlation. We're graphing average acceleration as a function of sine theta, right? Okay, so what we really want to do is we'd like to extrapolate this line out to where sine theta goes to what? Yeah, where it goes to 1, because let's look what happens. If this is if I want to,
Just get it. Get it out of there.
if I want to run this out to where I'm going to be, if I'm going to be approximating or guessing what the actual value of undiluted gravity is, right, without the ramp being there, wouldn't that be the case where I just make this thing vertical, right? Well, if I make it straight up and down, what's sine equal to? 1, right? The angle is 90 degrees, as close as I can get it when I'm moving this thing around. But if the angle goes to 90 degrees, the sine function, sine of 90, goes to 1, doesn't it, right? So we'd like to take this graph, so this represents essentially question, I think it was number 3, right? That's question 3 right there. But question 4 wants us to do something a little different. Question 4 wants us to extrapolate that line. So we're going to go down here, and we're going to change this to go out to 1. So sine theta goes to 1. So I'm going to make it 1.05. So it goes a little beyond that. And then up here, let's get rid of that. Up here, we need this to go a lot higher, don't we? Right? Because that line's going off. So let's make it go up to like, I don't know, 10.5, something like that. And now if I go back down here and I extrapolate this data, look what it does. Okay, now we can go out here to 1 and see what the value is at 1, right? What is roughly the data at 1? Well,
Looks like 9.8.
I think you can,
Couldn't you
No,
put
it's
a
like
tab in
9.
it?
yeah, I think you can, there's a way you can do this. Can you trace on here? What do you do? Let's see. Right here. There we go. See, look, I can do that. So I'll go out here to 1. Okay. How come, isn't that doing what it's supposed to do? Let's see. Oh, maybe that's not what I thought it was. Never mind. What is it? Oh, examine. Yeah, that was examine. I thought that was.
What did you want? White?
Yeah, I wanted to get what the Y value is. I thought that's what that thing did, but maybe I'm wrong.
Well, exit out of the top thing that you have right there.
That thing?
Yeah, try to redo it. See if
Okay.
you-
Man, I thought that's what this thing did. Do I have to click on it first or something?
Well, so when you click on it, it selects one of the data values.
Oh, I got you. Okay.
Well, what? Oh,
Is that working?
it still selects.
Oh, it selects a data value. Yeah, I got you. Darn it.
If you just put it-
Yeah, I can just go put it up there though. I think, can I just do that and get a value? Yeah, there it is. See, look, if I go up here, see right there? Look down at the bottom, look down here. See? It tells me the X and Y coordinates. So if I'm on the line up there,
Ooh, I was so close. I was
Oh, that
0.06
little
off.
I said
Right.
9.4.
see what I'm saying? So when it's at 1, we're at 9.44, right? And so what we end up getting then is our approximate value is a little bit low, isn't it? Right? Right, our approximate value is 9.41 roughly. What should it be? 9.8, right? Why do you suppose it would end up being a little bit low? And yours should end up being probably a little bit low. Yeah, there's going to be some friction, right? There's going to be some friction, and the friction is going to be more pronounced when the angle is at a lower, like when the angle is small, right? So you should expect, I mean, if this, really, realistically, if you think about the physics on this, you shouldn't expect to get a perfect value because those are not perfect carts. They're not truly frictionless. They're very low friction, but you should get an acceleration that extrapolates out to be something a little bit lower than 9.8. Do you think what's the danger of this? Real quick, I'll answer your question in just a second. What's the danger of making an extrapolation like that? Do you think? Look where all the data points are.
Oh, it's far-fetched.
It's a long ways away from the data, isn't it? So this is like the butterfly effect. Right? Any small change to these data points is going to change that line a little bit, right? Changing the line a little bit down there when you move far away, so when you're extrapolating a long ways away from the data, any slight tweak in the data is going to have a pretty pronounced effect on the extrapolation, isn't it?
Yeah.
So you'd have to take this with a little bit of a grain of salt. I mean, because that's a pretty extreme extrapolation. But it's not a bad way to do it. I mean, we took pretty good data. I mean, these things work. These motion detectors they're accurate, and it is pretty low friction. And so, I mean, it's not bad. I think you should reasonably get within 15% the value of gravity, which is pretty good. So, does that make sense? So that's how I think a lot of you guys were thinking that the slope of this line was going to give you gravity. That's really not it, right? That's not what you're doing. You're going to have to extrapolate out to this point. And if anybody figures out how to make that line over here, please tell me, because I'm not seeing it.
You won't get the acceleration of gravity right there.
From this?
Yeah.
Because the slope, think what the slope means. The slope is rise over run, so it's going to be the change in acceleration over the change in sine theta. That's not really representing gravity there.
Well, we got like almost the exact thing.
Yeah, and I think it's going to come out to be close. It's going to come out to be close, but that's sort of an accident in a way. Okay. Make sense?
Yeah. Wait, I have a question.
Yes.
So how did they figure out that it was actually 9.8 instead of something like this where you get friction?
How did we figure out it's exactly 9.8?
No, how did he? That one.
Oh, he didn't.
He didn't.
No, they didn't.
Did he have it close?
They were pretty close. Yeah, he just did lots of experiments to where he changed the angle, and people were smart. They kind of assumed that based on what the changes in the values were, they could make a fairly good approximation of what the frictional effects were. And yeah, but it was a long before we could actually measure what it was. We had to develop some instruments that could measure it with sufficient sensitivity, right? Okay. Make sense? Okay. All right.
All right.
Have at it.
Let's go. Yeah. We'll get over there. Oh my god. Do you have your keys?
I do.
I'm gonna lock the door.
Yep.
I missed one in each of the first 2 seconds.
Man, let's look at how that
So
works.
the last section I missed 5. So it should be like easy to get an A, right? Yeah. I would take it and it's 6. That was so upsetting. It's like,
I thought it was where you like miss a question that you get something.
yeah.
But she warns me, so then I put what I should for the first time, and then it's,
Yeah, it's the other time instead of the first time.
Hey, walk in here real quick. I got one more thing I'll show you. So here's, I was hoping I'd be able to find that vertical line, but all we've really got to do, if we want to know what the approximate value of the acceleration is go up to this equation and do what? Y equals mx plus b, and put in what value for x? 1. Exactly, right? So if you put in 1, you're going to get whatever that slope is plus your slight y-intercept, right? So it's going to be very close to that, right? It's going to be off by just a little bit, okay? Because the best fit line doesn't, because of friction, doesn't actually go through the origin, right? Okay, all right, there we go.
Hydra. Hydra. The little insects that we look at.